Hello and welcome everyone to today's developer coaching webinar. My name is Tara Van Cleve and I'm part of the technical marketing organization here at Oracle. So today you'll get to know the basics of vector tiles and H3 support in Oracle Database 23 AI, followed by a demo showcasing the simplicity and flexibility of these techniques. I'd also like to note that we are recording the webinar and you will receive the replay via the same email that you registered with for today's event after the event concludes. So if you have any questions, we have enabled the Q&A section of the Zoom and we'll answer them throughout the hour as well as leave some time at the end for any remaining open questions. Today's webinar will be presented by David Lapp, Senior Principal Product Manager for Oracle Spatial and Graph. So without further ado, David, take it away.
Thanks, Tara. I'm going to just share my camera for a moment here before I jump to my presentation and just say hello to everyone. Thank you so much for joining. And I see a bunch of names I know and a bunch of new names, and welcome. It's a pleasure to be presenting on the OCI Developer Coaching Series today. And so I'm going to be talking about some new features in Oracle Database 23 AI that are specifically developer oriented. And before I jump in, I just want to try to do a very quick show of hands for a couple things that'll help me orient the emphasis today. So there's a raise your hand button somewhere in the Zoom panel. And the first question I just wanted to ask folks was if you could raise your hand if you're someone that's already sort of involved in the geospatial realm, whether that's at the database level, the application development level, you name it. I just want to see who's sort of already uh, generally familiar with this domain. And I'm seeing a few hands go up, and that is a whole bunch of hands going up. So that's very valuable. Awesome. Okay. So I asked about the spatial domain because that's the domain that this is all about today, in particular about these new features we have in 23 AI database for developers for sort of geospatial mapping and analysis. And so at Oracle, if you're not familiar with the Oracle geospatial footprint, we are a integral part of Oracle database and have been for a long time. Our sort of guiding principle is that everything happens somewhere, and we are the feature in the Oracle ecosystem that really brings that to life. So we're a feature of the converged Oracle database. We live alongside the other converged features of the database, like Graph and like in database JSON and so on and so forth. We're just another one of those converged features, and we are there to allow you to use location as a key for analyzing and relating otherwise disparate information. And of course, to do that in the context of a business process. At its most fundamental, the Oracle database allows you to store basic point, line, and polygon geometries in a native data type, and you can see examples of what those would represent here. And then most importantly, to be able to answer important business related questions in terms of spatial measurements and spatial relationships between those types of objects. And you can see some of the examples of questions on the right that you're able to answer. But beyond those basic capabilities of storing and dealing with points, lines, and polygons, Oracle Spatial has grown over the decades to support lots of other advanced capabilities, like dealing with a variety of 3D and raster-based data sets, connected networks. And again, it's all about, at the end of the day, answering the kinds of questions that you see on the right. And that's the value of this. And there's more and lots of other features that I don't have time to even list here, but every one of these goes above and beyond just storing and processing and analyzing basic geospatial data. It gets into additional, sometimes domain-specific capabilities around spatial data. And again, I focus really on the kinds of questions that you see on the right that we're able to answer. The other key thing to know about Oracle Spatial, if you're coming at this new, is that not only are we a native feature of the converged database that allows you within the database to manage, process geospatial data and answer important business questions, but Oracle Spatial is also uniquely supported across the geospatial industry because we've been at this for many decades. So over on the right or on the left, I'm sorry, you see the ecosystem of the Oracle ecosystem of sort of APIs and tooling to be able to work as a developer with Oracle Spatial, whether, as I'll be showing you today, working with SQL, working with Oracle REST Data Services or ORDS, but there's lots of other developer-oriented access points, as well as Oracle Spatial Studio, which is our tool for no-code access. And over on the right is really the whole geospatial industry, which I'm showing in some samples of. But all of these technologies and tools and platforms all natively support Oracle Spatial. So it is a truly unique geospatial data management, processing, and analysis platform for the whole industry. The things that are the key new capabilities in Oracle Database 23 AI are broken into these three categories. There's features that make it easier for new users to jump in, simplifying some syntax. There's developer-oriented features, three key ones, as you can see here, and it's the ones in red which are the focus of today's session. So these developer-oriented features are what I'm going to be focusing on today. And then you see there's a third category of new features in 23 AI around advanced 3D spatial analysis. And that's outside the scope of what we're talking about today, but that's another new and exciting 23 AI enhancement. Okay, that's the preamble, and now to get into the first topic. So we're going to talk about vector tiles in H3, and of course define what they are, and then get into them. So first, uh, what vector tiles provide is a highly optimized, compressed format that is supported by all modern web mapping libraries and toolkits. And what this new capability is that we have is to directly serve up and return Oracle spatial data, both the geometry and the attributes, in this vector tile format, which again is universally supported across modern developer toolkits. Um, I want to make a special note. You see on the top right that vector tiles has the word vector in it. And when we hear the word vector now, we all immediately turn to vector embedding and LLMs and AI search and all that sort of stuff. And that's not what we're talking about. So in this context, vector tiles means specifically these spatial vector tiles, which is a format for serving geospatial data. And just turning back here, once I'm, important thing here is that instead of needing a whole separate tier of technology to do this processing, by having this in the database, we've really simplified the overall architecture of serving geospatial data to modern web clients. So what are vector tiles? They are a compressed protocol buffer or protobuf format, binary format of geospatial data based on a global hierarchical system that I'll sort of demonstrate in a second. And they have lots of benefits, lots of really important benefits in terms of their performance and how they can scale and how widely adopted they are. And there's a link that we're going to share that'll point you to where you can read a little bit more about the vector tile spec. But I just want to open up a page here that'll just give you a feel for what the tiling scheme looks like for vector tiles. So here I'm showing nothing but a base map right now, but the boundaries that you see in red are the boundaries of vector tiles. And these are a standard tiling scheme. On the upper left corner of each tile, you see the numbers with the slashes between them. So 2/1/1. The first number is the zoom level. The second number is the X axis, and the third number is the Y axis. So this giant tile here is zoom level 2, tile 1/1. As I start to zoom in, we will of course see now I'm down to zoom level 4, and now I'm down to zoom level 6, and I can keep zooming and zooming and zooming. And we're going to see this standard universally adopted set of Z, X, and Y indexes for each of these tiles. And so what's contained in each tile is basically a vector tile or multiple vector tiles with the geometry and attribute data. So that's what the tiling scheme looks like. And what we're doing with Spatial now in 23 AI is serving Oracle Spatial content in this format that all web map clients are able to consume. All right. So this is really what the simplification looks like in 23 AI. So before 23 AI, it was possible to serve the data in this way. In fact, we've been doing it with mid-tier componentry before 23 AI, but now what's simple is that all you need is a Oracle database, and you have everything you need to have a whole vector tile service stood up. And again, the value here is that when you use this 23 AI capability, serve vector tiles, you can use Oracle REST Data Services or ORDS to expose it as a REST service, and that's all part of the converged database environment. And you then have what you need for any standard, popular modern web mapping client to consume that data. So really what I want to focus on here today is showing stuff. So let's jump in. All right, so I'm going to actually at the database level to start at the database level to hopefully make it really clear exactly what's going on here. And all right, so I am connected. So I'm going to start with a table here called Boston Buildings. And if I just describe that table, and first I'm going to pick my connection. All right, so, and let me just clear, so I have a clear palette here. So let me describe this table. And here I have a table. It includes a geometry for each building. And then we've got the area and a few ID columns. And and skip that. Now, the new function in 23 AI under the SDO util or utilities package is get vector tile. And get vector tile accepts the table that you want to serve vector tiles from, the geometry column, because there could be multiple geometry columns. So we need to know which one is the column we want to stream as the geometries. And then remember I showed that tiling scheme. And so a vector tile, an individual vector tile will be based on the zoom level, the X and the Y for that individual tile. And then which attributes values should be encoded within the vector tiles. So if I wanted to manually generate one single vector tile at a particular zoom X and Y level, I can run this statement. And the result's going to be something that's not all that interesting to look at here at the command line because it's a blob, because a vector tile is this binary compressed proto-buff payload basically that has the encoded geometry and geometries and attributes. This brings me to the key point here that because vector tiles are this binary format that is designed to be consumed by web mapping apps, the whole purpose and value of all these features that I'm showing are really pointedly for developers. It's not that you're going to sit here and use this for the purpose of doing ad hoc SQL-based analysis. So I'm not sure. So this will become more interesting when we get to the web client that's consuming this. But I first want to make sure that the underlying SQL makes sense. So here we have one manually selected sort of hardwired vector tile based on picking the zoom and X and the Y. That's if I just want all the geometries from Boston buildings that are within this tile, and I get my vector tile. Now, what if I wanted to apply some predicate or some filter on what I get back? Well, there's an additional parameter that I can include in the request, which is simple predicate. And a simple predicate will include basically like an array of predicate values. Here, my array, I only have one, which I'm going to say I want the buildings where the area square feet is greater than 10,000 square feet. And you can have multiples that are multiple predicates that'll be assembled in an and fashion. But this is an easy way to say, now I want a vector tile at this ZXY value for only these large buildings. Now, I want everyone to immediately look at what I'm doing and think about it in the context, not of just a query like this, but how you would operationalize this by having it behind a service where all these values are built through parameters. Users are maybe specifying a square foot tolerance that they want to see buildings for. Users are panning and zooming around a map. So these zoom X and Y values are always going to be generated by an application automatically, not someone writing queries like this. But when you strip all that away and get down to the underlying database operation, this is what's happening. So this is a simple predicate. What if we want a more involved predicate? A predicate that's not really just a predicate, but a whole query. It might be some join query that's going to return a bunch of geometries. I want vector tiles for them. Well, there is also a capability to support that, where instead of just running get vector tile on a table, we perform get vector tile and we perform it on a cursor. And within that cursor, we have a query. And it's the result of this query that we want to have vector tiles for. So in this particular case, my query is, I want all the buildings that are within 10,000, where the area is greater than 10,000 square feet, and where those buildings are within 1 kilometer of a coordinate, of a particular coordinate. That's just, I made up a query. So it's not just a predicate, it's actually a spatial query, a within distance query, to give me only a certain set of buildings in proximity of a location. Well, we have this construct that allows you to do that, and it actually involves another vector tile oriented function, which allows you to get the tile extent that you're looking for, and then performing a sort of a secondary filter on the query result to just give you that result within the tile you're looking for. If that was hard to comprehend, that mumbo jumbo I just said, there's examples of this and it's in the documentation. I'm not going to focus too much on it, other than just wanting you to know that if you go beyond serving vector tiles for tables or tables with simple predicates to serving vector tiles for more complex analysis results, you can do that. And just to show that this runs, I can run this query, and this blob here would be the vector tile, one vector tile for this query result. And I'll show what this looks like in an application later. So now, of course, we can, for applications, we would be doing the exact same thing, but we'd be doing it with like runtime parameters. So if I ran a statement with bind variables like I'm doing right here, I could populate these variables like an application would be responsible for collecting and submitting, and then I'd get a blob back. I'm not going to bother running that. One other, before I jump into showing what it looks like in an application, one other new feature that we've added is the ability not only to get vector tiles from spatial data, but to have a auto-maintained vector tile cache, so that you can have the system accumulate vector tile results, and then when requests are made for those vector tiles, don't regenerate them. Get them from the cache. If the underlying data changes, automatically update the cache. Only build the cache to a certain zoom level if you want to not take up too much space. Lots of control over how it works. So here's what it looks like. I'm going to start by saying, well, in case I had already been caching Boston buildings before, I want to clear it to have a fresh start. And then I'm going to sort of disable everything. I'm sort of resetting my environment. So we have a table called SDO vector tile cache info, which would list tile caches that are in effect. Right now, you see the result is empty. I have none. Nothing's being cached right now. Now I'm going to say enable the vector tile cache on the Boston buildings table for the column called geometry, which means that once this is enabled, any vector tile request, the result will be cached until I tell it to purge cache. Any subsequent request will get the result from the cache. Now that I've done that, if I run that same statement saying, show me the vector tile cache info, this table and this column are listed. It means like the geometry in Boston buildings is now turned on for caching. Now, is there any cache that's been developed? I haven't made any requests yet for vector tiles. So if I look at the table, SDO vector cache table, where table is Boston buildings, this is the table that would actually have the cached vector tiles. I haven't made any requests yet, so the cache has not been seeded. Well, I'm going to go through a little loop now, and for a few iterations of building IDs, structure IDs, I'm just going to go through and request building some vector tile cache content. So I'm going to run get vector tiles for Boston buildings, column geometry. I'm going to do that for tile zoom 17, this particular X, and then a few Y values. In other words, I'm going to build a few tiles. So let me just run this statement. And so that's just going to loop through and build a few vector tiles for buildings. And then now we'll go back to the cache. And now here are and you can see tile zoom 17, tile X, that's what these are. And the tile Ys that I built were the loop that I went through. So I built 6 vector tiles in cache. All right. Vector cache, go back and run this again. All right, so now I can purge that cache and take a look here again. And now that cache is empty so that if another request was made, it would have to rebuild the cache. So that's the general idea here is that you'll speed things up a lot by virtue of strategically pre-building vector tile cache. So that's all the view from the SQL level so that when I show you how you expose this for applications, it will make sense. So now let's jump over to Oracle REST Data Services where we actually do the provisioning of what I just showed you as services for an application. So I'm going to assume that not everyone is familiar with Oracle REST Data Services. So for those that are not, very simply, Oracle REST Data Services is a capability that's built into the database and through a sort of a mid-tier app that allows you to REST enable anything you're doing in the database, whether it's data analyses, ad hoc SQL, tables, views. If it's in the database or generated from the database, it can be REST enabled through Oracle REST Data Services. And in the Oracle Autonomous Database environment, it's one of the tools that's automatically provisioned for you. Nothing to install or configure, it's automatically there. So just another one of the sort of the beautiful aspects of Spatial being part of the database, it just works seamlessly with Oracle REST Data Services as one of the other converged features. And the way that it works is as follows. You start with modules, which are like essentially APIs. And so just to create something from scratch, also say create module. And my module will be called my API. And the endpoint will look like that. And just for this moment, I'm not going to protect it because it's only going to be here for a moment. So let me just create an API. Then within an API, you have templates, and templates are the specific endpoints. So for this module, for this API, so my API, I'll have an endpoint called my endpoint, and this is where you can supply parameters that are supplied at runtime. So I'm going to have my endpoint. Now that you have an endpoint, you have handlers, and handlers are the logic that handles get, post, put, and delete requests. So I'm going to create a handler. It's going to be a get handler, and it'll be a collection query, and I will write a query here that will be the handler. So this is going to be what is run when a REST request is submitted, and I'll describe what this is in a moment. So here's my handler. So this is just SQL statement. So what I'm going to do is run a SQL statement, and that SQL statement is going to select from Boston buildings for a particular building ID, and it's going to return the geometry as GeoJSON and give me the area of that building. I mean, just a basic query. I can test the query by running it, and I've got a placeholder for ID. So I'll say ID4, and I'll get back, you can see a GeoJSON geometry and area. That's just the query. But what's interesting is what this is for is to actually publish this as a as a service. So now that I've done this, I can now grab this endpoint and I'll just paste it in here and supply a value, and that's it. it's got some extra stuff here for pagination that I didn't turn off, but here is the result, you know. In fact, if I just go to the raw data and pretty print, so here's my area, here's my geometry. I have a REST API that's doing, it's actually doing a little spatial work here, but it's any SQL. So I mean, that's it. I just created a REST API using Oracle REST Data Services. So all I'm going to do, show you that I've done the exact same thing with our vector tile stuff. So I created a module here called vector tiles. It's like my vector tile API. And the first thing I'm going to do is I created a template to return buildings as vector tiles. And I created one handler that should handle GET requests. And the GET request for buildings looks like this. This is going to look very familiar. It's a GET vector tile query. Now, one important aspect of Oracle REST Data Services is that you can have it return the results of a handler by default using the default JSON format of Oracle REST Data Services. It'll automatically put results in a JSON format. You can also tell Oracle REST Data Services to not put it into any format, just to stream the result as is with no post-processing. And that's what I've done here. And that's why I've actually putting my own header at the top of this result, and the result is being streamed directly as is. So what you can see is exactly what I showed in SQL in the worksheet. Get vector tile from Boston Buildings, column geometry. The Z, X, and Y are runtime parameters. And I've got two attributes, the structure ID and the area are what I'm going to return. This will return a blob if I run it. So, okay. So, um, so what I'm going to do is grab this endpoint right here and copy it. And what happens if I just run this endpoint here, and then I'll just supply the Z, X, and Y values. Uh, so I actually have these values, and we can see right here that 48490.pbf, that is a vector tile that's being streamed and returned. PBF stands for protocol buffer. So that is me manually assembling a REST call by specifying a Z, X, and Y and returning a vector tile. So what this looks like in an application is the following. So let me open up an application. Application is a little bit more than it is. It's just a web page using a web mapping client. So now we've got a web page here that's displaying those buildings, and they're being color coded using one of the attributes. As I zoom in here, you can see that every one of these colored shapes is a building. And now if you remember that whole vector tiling scheme thing, you can see that as I zoom in and out, what's happening here is I just have requests somehow being made to that endpoint to get vector tiles. Well, how is that request being made? It's being made as follows. So if I look at the page source here, so here is the totality of that web page, and I'm just in this case using the MapLibre client. Well, that's the one that we tend to use a lot here internally, but any modern web mapping client will work. And in these clients, you're able to load a map and define a layer in the map and define the source of that layer. In this case, I'm going to have a buildings layer. It's a vector layer, meaning vector tiles. And this is all I have to do in the client. I supply the endpoint with placeholders for Z, X, and Y. And the client automatically assembles and streams the request, automatically populating the Z, X, and Y based on the user's interactions. That's what the client does. And our REST API that we just looked at has that signature built in. So it's expecting calls that look like this. And then just have an on-click function that knows how to grab the client, the web map clients know how to get the properties out of vector tiles, like the ID, and I'm rounding the area in square feet. So, super simple example, but this is what it does. And here's what the requests look like. So if I go to the network traffic here and zoom out, and you see these sorts of requests right here. If we look at one of these requests, this request here, it's exactly, the kind of request that I put in manually. I didn't, it's the client, it's the web mapping client that's assembling all these requests, basically sending all the requests that it needs for all the Z, X, Y values to assemble the map based on whatever the user's sort of footprint is, where they've panned and zoomed to. So let's look next at an example that applies a little bit more logic in here. So that's just the basic ZXY example. So I also have an example that does a distance calculation. So in this case, we also have a handler here, and and remember I said that if you want to serve vector tiles from the results of a query, not just a simple predicate, but a query, then we have this get vector tile that is fed by a cursor that has both the query you want to run and the vector tile functionality that knows how to determine at every request what's the sort of the total outline or envelope of the request area, and then it gets the results of the query that you want, which is going to be like a proximity query, and then combines that with only getting the results back that are within the envelope area of the vector tiles requested. So again, this one's a little bit of a, for me anyway, this one was a little bit hard to completely understand. I mean, it works beautifully, but if you experiment with it, you'll see how it works. Here I've got the query I want to run, and here is where I'm only going to get the results of that query that are within the envelope of the requested vector tile area. So here, in this case, I'm also just going to be supplying I'm going to be supplying the Z, X, and Y, but I'm also going to be supplying the distance I want to search and Z, X, and Y, distance I want to search from a where. Okay, sorry. So in this case, I'm going to supply, I want to get all the vector tiles for the buildings that are within a certain distance of some other building. So I'm going to pick a building and a distance, and then I'm going to get all of the vector tiles that are within some distance of that building. So give me the geometry of the building fed by an ID, and then here give me all the other buildings that are within some distance of that building, and I want the vector tiles from that result. And so here's an example that does that. And then we'll look at the code. So buildings near building. So I'm going to run this. The spatial query is running. And now instead of all the buildings, you can see I just get these buildings, and they stop when I reach a certain distance away from the building that I selected. And in this case, it's the request in the JavaScript, the request for these vector tiles was just a request that includes those additional parameters. So for example, more tools, page source, and now you can see that my request was here. In this case, I just hardwired saying buildings, and then here's a building ID and a distance, and then Z, X, and Y. Now, of course, if this was a real application, was doing things in a flexible way, I'd have something in the UI, some user control to be able to say, select a building somehow and have a slider for the distance and have this whole thing be dynamic. And that's where your mind should go when you see something like this. This is just like a hello world example where I'm hardwiring some things in. So that is the vector tile story, and I still need to get to the H3 part of it. So I'm going to transition now back to here. So you saw some of what we do with vector tiles, how we deal with them in the database, how we can cache them, how we can access them, how they can be sort of flexible in what content you're serving up. Now H3. So next topic, H3 stands for hexagonal hierarchical spatial indexing. And as you can see in the picture on the right, it is really just a hierarchical scheme of hexagons, hexagons and hexagons and hexagon. Each hexagon sort of explodes out into a bunch of nested hexagons and so on and so forth. It's really interesting actually to read about the background. This was developed by Uber. And I've got the link to their blog where they describe the whole evolution of it and the benefits of it and everything. But just like vector tiles, this is a widely adopted scheme for indexing spatial data for a variety of use cases that I'll describe. So, what does this scheme sort of look like, and how are these hexagons identified? And I'm going to jump into this h3geo.org page here, where we can um, see a map covered by H3 hexagons. In fact, like three nested levels of those hexagons. So if I click on some area in this map, it's showing me the unique ID of that hexagonal cell this is at resolution 1, and I could click on it again and zoom in again to the next level. Now this is a hexagon at level 2. I've got its ID and so on and so forth. I could keep drilling down to hexagons and hexagons, and I could actually show how each of these hexagons here are all part of hexagons at this particular level, and they drill down and down and down and down. So that and the beauty here is that this is a like industry-wide, well-adopted scheme, so that these unique cell identifiers, sort of everyone agrees on what they are and what their footprints are. So that's what the H3 scheme looks like here. And and to hop back here, so that's what sort of H3 indexes are. What are they useful for? Well, the two main use cases. Number one, it allows you a scheme or a hierarchy, a geographic hierarchy, for the purpose of aggregating and summarizing data, whereby you take, generally speaking, most commonly point data, and you summarize it into these hexagons, whether that summary is a count of how many items are in it or some statistical uh, aggregate, average, min, max, whatever. And the point is that because these hexagons are nested and hierarchical, you can always look at things at the right level of resolution for the scale that you're looking at. So when you're zoomed way, way, way out, you can look at hexagons at a big, broad level. And then when you're looking at things at a giant scale, zoomed way in, you can look at much more fine-grained hexagons and always maintain sort of a reasonable size of a hexagon on the screen as you zoom in and out. So that aggregate visualizing aggregations is one pivotal use case. And the other pivotal use case is for the purpose of integrating data. And because of the fact that you have this universally recognized scheme of uniquely identified hexagons at different levels of resolution, you can take disparate data sets that have nothing in common other than location relationships, and you can join them, like do a database join between them based on their common presence within H3 cells. So really what that means is you can enrich data with an H3 key, enrich multiple data sets with an H3 key, and use that key as a join, keeping in mind that the resolution or the zoom level of the hexagons themselves will determine sort of how wide of a net are you casting to group things together. So it's the visualizing aggregations and the integration that's the key thing. The operations that we have in the database in 23AI that we've added are to be able to start with a coordinate or a geometry and get the H3 cell ID for it based on a given resolution. Because remember, any point in the Earth is going to be part of a giant hexagon and then smaller and smaller hexagons at different resolutions. So you specify the resolution, give me a location, I'll tell you the H3 key out of the database. The inverse too, you tell me an H3 cell ID, we'll give you the geometry, the SDO geometry of that cell boundary. The other thing we do now is that we will take a table of point data and a given threshold of resolutions, and we will generate a whole table, which is an H3 summary table. So a table that has a summary of that data, whether you want average or count of items, and will populate a whole table with all the H3 keys and aggregate values. And the main purpose for that is for the function we have that will take that summary table and return it in vector tile format, just like we've been talking about with regular other tables, so that can be consumed in the H3 hexagons can be consumed in an app. And that's what I'm going to show all these things next. And over on the right here is just sort of a screenshot out of the documentation of just H3 functions to make it clear that what's on this picture on the left are the main sort of user developer facing things that we have for H3 in the database, but there's a lot of other capabilities that we have to work with H3 for other maybe edge cases that are outside of what I've talked about. All right, so jumping now into seeing what all this looks like. So let's start with coming back to SQL quickly. All right, so the first thing we have is to get a boundary from an H3 ID. So let's get an H3 ID. So here I am. I'll just pick, I'll just pick this one. Or actually, if I want to get rid of all this, so let me just click somewhere. So I click here. Here is at whatever level of resolution this is. Where are we? So this is at resolution 3. Here's a H3 cell. So come back to here. So I'll run this statement and populate the H3 cell here. And what do I get back? I get back an SDO geometry. So this is the hexagonal geometry associated with that H3 cell, which basically means, this app we're looking at here, we could be doing the exact same thing, just using Oracle database and Oracle REST data services and HTML and the web mapping client, because that's really what's going on here. So that's an example of getting the geometry of a cell. Then the next thing would be to get the key based on longitude, latitude, and resolution. So if I want to generate the key, here's a longitude, a latitude, and a H3 resolution. And I zoom back, and now here's the H3 key from that, which means that, again, like if a user's clicking around or you have any business process that needs to know for what is the H3 key at a given level, that's just a pure SQL operation. So now what does it look like to do that integration between data? Now, this was an opportunity to show that simplification that we have now in 23 AI for new users. And I'm just going to quickly reset my data so I can start from scratch. All right, so I'm going to start with a table that has no geometry in it here, but it has coordinates. This is a very common way for people to start, maybe with some data that you want to ultimately do the stuff I'm doing, but you don't have nothing but coordinates, no geometries. So here's how simple it is in 23 AI now. So I'm going to alter this table and add a geometry column. Now, because this is longitude, latitude, I can populate these geometries now with our simplified constructor, which is just SGO geometry, longitude, latitude. It used to be more complicated. The geometry constructor had a bunch of other parameters that you had to understand. Now it's just SDO geometry, longitude, latitude. So there I've updated my data. Now, the other thing that's easier in 23 AI is that I can now immediately, I've got data in this table, I can create a spatial index simply by running the spatial index statement without having to pre-populate spatial metadata, which was also another like little kind of complicated thing. That was it. What I just did was took a table with coordinates and now have it fully configured with geometries that are indexed and ready to go. It's pretty simple. So now let's do this integration thing that I mentioned as a use case. So what I'm going to do is here I've got query that's getting the H3 keys for each of the rows of data here. So I could run this. This is for my new, and I'm going to pick up for all these H3 queries, I've got a parameter to specify the resolution because remember, everything is based on what level of resolution or zooming into these H3 hexagons you want. I'll say resolution 3. So all I've done here in this inner query is for each row, give me the H3 key for each of these points. But I'd actually like to get the data with the H3 key and the H3, the geometry, the actual hexagon geometry for each. So I'm first doing like a within statement, a width statement, and then I'm gonna, so that I don't have to get the key twice, I'm using a width and then a select to get the hexagon with H3 boundary, this H3 boundary function. Again, I'll pick resolution 3, and now I've got for every row of data in this table of facilities, these are just facility locations, I've got the H3 key and the hexagon geometry. So that's table 1. You know, I haven't done any integration of anything yet. I just showed how you can take a table, get its the H3 keys from and the geometries if you want for the hexagons. Now for integration. I have a totally unrelated data set of wildfire locations. So this is a table here. I already have a geometry in this one. And these are USGS wildfires from across multiple years. And I can do the same exact thing here where for every row at resolution 3, for every one of these fires, here's the H3 key, here's the geometry of the hexagon. Now, what's interesting is I will sort of on the fly, I'll do a join between the two based on H3 key. Now, in reality, you would probably not do this all in a on the fly view sort of approach like this. You would generally enrich your data and populate it with a new column and with the H3 keys so that you have actual key values, columns to join on. I just want to do this with a all in one query just to show you all the moving parts in one place. So I'm only going to do this on 1,000 rows of each. So like 1,000 facility locations, 1,000 fires, and I want to join them based on H3 key. So here I've got the two queries that I had run previously to get the H3 key from the facilities, the H3 key from the fires, and then join the two based on a common H3 key. And I run this again, I'll pick resolution 3 again. And now I've got a join. I'm joining, and I've ordered this by facility name. So these are all rows of facility name and a fire that occupy the same H3 key. So this is just literally joining facilities and fires based on H3 at a given level of resolution. Next, what I'll do is I will do what's maybe a little bit more likely is sort of an integrated aggregation. So for each one of the H3 hexagons that have been joined together in this way, I want to see a summary of the facilities and the fires within them. And so H3 key order by facility name. Actually, no. In this case, I'm just going to do the exact same thing I just did, but add the geometry to the result. So now I've just got, again, the hexagon, facility, fire, and the boundary polygon. But what I want to do here now is to do an aggregation. So for each of these hexagons where the join occurs, I want to summarize the fires and the facilities. And in this case, I'm just going to do a count of each. So I run this now at resolution 3, and I've got a hexagon, how many facilities, how many fires, and the hexagon shape itself. So as you can see, this is now something I could immediately start to put behind a service, stream to a map, visualize these hexagons. All right, now the last thing before I jump to the showing this thing in the web in a browser is the following. I mentioned that for the purpose of streaming vector tiles, streaming now, before I go on, I just want to make it clear what we've got at this point using H3 is sort of a example, like here's some data that's been integrated based on H3 and some aggregation. I've got H3 polygons. The resolution could be a parameter, all that kind of stuff. That's enough right there for me to create a REST endpoint and start to stream this into an app. What I want to turn to is this summary table thing that I described, where we create a summary of an H3 summary with all the different resolutions you want and all the aggregated values that are ready to stream as vector tiles, sort of in a turnkey fashion. So I'm going to start by kind of resetting my environment here, and let me drop the existing table and delete the metadata for this table. Okay, so here's the function that we have to create this H3 summary table. It's called in the SDO util or utility package H3 sum for summary create table. Tell it what's the table. This is physically going to create a new table in the database. What should that table be called? TRI stands for Toxic Release Inventory. That's what these facilities are. These are facilities that the US EPA monitors for toxic release. So I'm going to create a TRI H3 table. What table should it be based on? My facilities table, which is this TRI 2017 US table, the geometry column, and the aggregation. Now here I'm just going to do count, but the aggregation, you could do different statistical aggregations. And then what's the maximum resolution? I only want to go down to H3 resolution 5 because I want this to be quick. I don't want to generate a gazillion rows in this H3 summary for the tiny, tiny hexagons. So I'm just going to run this, and this is now building the H3, the TRI H3 table, which is my H3 summary table. So that's done. Now we can look at it. This is the table that was just built a second ago. So all the way zoomed out at 0 resolution, here are the keys, and here are the counts of the numbers of facilities in each of those hexagons. Now I'm at resolution 1. Here are the keys. Here are the counts. And as we go down and down and down, we'll get to deeper resolution and counts. Now, all we have in here is the resolution, the key, and the count. Um, you could, of course, assemble your own endpoints by figuring out what the geometries are for each of these keys and streaming them, but we have a convenience function that does that automatically, H3 sum vector tile. H3 sum vector tile is the function that will point to a H3 summary table like this and stream the results as vector tiles, automatically getting the hexagon geometries based on the key so that you don't have to. So in this case, you just specify the H3 summary table. I just created this TRI H3, and you specify the H3 resolution, which is 5, and then a vector tile ZXY, like any other vector tile request. And when you run this, you get a blob. You get this binary vector tile, which again is what a web client is ready to consume. So generally, what you would do is, so this is hardwiring some values, but once again, this is something that you want to create a REST endpoint for, and then have the client automatically supplying the zoom levels that you automatically supplying the Z, X, and Y based on the user moving around. But what about the level number? How do you know in the request what level number? Well, one approach is you can say, like I've done in this case, that the level number or the resolution of hexagons should be a function of my zoom level in the map. So in other words, the more I zoom in on the map, the deeper the resolution of hexagons I want. And the more I zoom out, I want to go to a higher level of hexagon. So here I've got an example where I've done that manually, but we also have a feature that has gives you an automatic, sort of does that automatically, just to make sure that the hexagons are always a reasonable size on the screen. So let's see, this is going to be demo data, I believe. So what this endpoint looks like is the following. So let me go to REST, go to my modules. I've got a demo module here within which I have an H3 example for wildfire locations. So here's an H3 endpoint, exactly like we were looking at before. And here you can see the handler. And the very first thing, again, because I'm using that option that Oracle REST Data Services has for just streaming, for just streaming the results back, I'm providing manually the header to say that this is a vector tile result. And then my operation is to run H3 sum vector tile. In this case, I've got an H3 table here. for wildfires, I'm manually specifying saying that based on the zoom level that a user is in the map, that's what determines what resolution of hexagons I want. And then the Z, X, and Y are coming from the client. And then uh, here's what the app looks like. So I've got wildfires. Um, so you see these hexagons start to pop up. And then you'll see as I zoom out, they, they're bigger on the ground, meaning it's a lower resolution. And the resolution or the size of those hexagons on the ground was based on my logic saying if I zoom into a given zoom level, I want to jump to the next resolution of hexagons. And in this case, my attribute is just count. So this is the number of wildfires inside each of these hexagons. And the usefulness here is that you can, as you zoom in, it's sort of like a clustering thing. As you zoom in, you sort of explode the hexagons out. So if you see a hotspot area, you can zoom in to find out where the concentration really is. But this is the behavior, and then once again, the uh, the requests look like look like this. So this is just another Oracle REST Data Services endpoint for vector tiles, where the client automatically knows how to fulfill the Z, X, and Y values. But in this case, instead of showing buildings like I showed before, we're showing hexagons. So again, like the takeaway here is that extremely useful both for visualization like this, as well as for integrating data based on these common keys. And and that is the top of the hour. And I've got some links here in this deck, and everything's being recorded. It'll be shared. Um, but there's some useful links here. And from I'm saying portal, sort of our homepage for Oracle Spatial, there's links to everything else, including the documentation. And within the documentation, that I've got opened right here. There's a whole section here on, vector tiles and a section on H3. And then, of course, as always, all of the actual API information is under reference information. And I was focusing on this SDO util because that's where the vector tile and H3 stuff is. So under SDO util, you'll scroll down and then start to see a whole bunch of stuff starting with H3 and also the vector tile functions. So we really hope that folks take advantage of this because what it means at the end of the day is a simplified architecture, less independent moving parts and deployments because the database can handle like everything up to and including provisioning the APIs and endpoints for standard modern applications to consume. So I'm going to stop it at that point, open it up for any questions or any unanswered Q&A.
All right, I think we covered everything. So thanks so much.